So let's extend our use of synthetic division and apply it to a couple new things, including the factor theorem, rational zeros theorem, as well as the conjugate zeros theorem. So our factor theorem is very similar to what we looked at previously with our remainder theorem, in that when we do synthetic division with a specific value of k, we know that if our remainder is 0, we know that k is a 0. And similarly, if we do synthetic division with that value of k, the factor that corresponds with that value of k is also a factor if the remainder is 0. And so we're going to apply it with the same context and just extend that understanding of what that factor represents. So we're going to use synthetic division in our factor theorem to determine whether or not x minus 5 is a factor of this given cubic polynomial. And so the way that we do that is again with the synthetic division. And since they give us a factor, we don't know what k is yet, and we have to identify that k is going to be 5 because that is the corresponding 0. If x minus 5 equals 0, x equals 5, and so that's the value we're using for our synthetic division. So 5 is our value of k, and we're going to set up our synthetic algorithm. And we're going to go through and we're going to actually solve the synthetic division. And again, we're looking for a remainder of 0. If we have a remainder of 0, then we know that x minus 5 is a factor. We also know that 5 is a 0. So bring down the 1, we multiply, and then we add, and then we multiply, and then we add, and then we multiply, and then we add. And because we get a remainder of 0, and so again, a remainder of 0, that means that x minus 5 is a factor. And it also means that 5 is a 0. Through that transitive property, we also know that 5 is a 0. All right, so we're going to do the same thing. We're going to check the next one. Again, our value of k is -1. We have a sign switch here. So we're going to set up -1 inside our synthetic division. We're going to bring down the first number. We're going to multiply. And then we're going to add. And then we're going to multiply. And then we're going to add. And we're going to multiply. Then we're going to add. And since our remainder is not 0, we know that x plus 1 is not a factor. We know that x plus 1 is not a factor. So again, these are just simple yes-no questions, and we're using the synthetic division to justify our response. So let's continue this a little bit more. Now what we're going to do is we're going to factor this cubic polynomial completely, given that -7 is a 0. So since they told us one of the zeros, we know that if we do our synthetic division using -7 as our k value, that we're going to get a remainder of 0. It has to happen. So we'll use that as a way to check to make sure our answer is correct. So we'll set up our synthetic division. And then something really neat is going to happen after we do it. We know we have to get this remainder of 0, which is really helpful for us that we did get the remainder of 0. We know that our answer is correct. We know that -7 is 0, which they've already told us. But more importantly, what this does is it gives us a quotient. And this quotient right here, there we go. This quotient right here is 8x squared plus 14x minus 15. Now remember, our original goal was to factor. So now that we have a quadratic equation, we can factor our quadratic. So we're looking for a product of 8 times -15, which is -120. That gives us a sum of 14. So we can check our factor pairs. Negative 120 divided by x. Check our factor pairs. We want to sum 14. And so we'll look and we'll see that, okay, well 6 and negative 20 give me negative 14. So therefore, a negative 6 and a positive 20 will give me positive 14. Then we can do our factor by grouping. Once we've factored out our quadratic, now we have our factors for the quadratic, but we need the factors for the cubic. And so how do we get that third factor? Well, because if I multiply these together, I only get back to the quadratic. I need to get all the way back to the cubic. So these are my first two, or my last two factors. The third factor comes from negative 7. The third factor will come from negative 7. And we have to think about, okay, well, if negative 7 is one of my zeros, what factor would give me that 0? And we just need to solve and get everything on one side of the equation. So if we add 7 to both sides, we get x plus 7 equals 0, and that is the third factor. So our three factors are x plus 7, which we got from the original 0, and then 4x minus 3 and 2x plus 5 that we got from factoring the quotient. So we've got all of our factors. Now, given that information, if we also wanted the zeros, we could set each of our factors equal to 0 and solve for them, and we could also identify all three zeros. So make sure that you're paying really close attention to the directions. Sometimes they'll ask for the additional factors. Sometimes they'll ask for all the factors. Make sure you are answering the question and providing the information that needs to be given. So we're going to do it again, but now we have a complex number. We have 3i, and this leads into our complex conjugates. With our conjugates theorem. When we are given a 0 that is non-real, such as anything in the form a plus bi, again, this is going to be an a value of 0, so we just have 3i, that's our b value. Non-real zeros come in pairs. They're conjugate pairs. The conjugate pair would be a minus bi. So if we have 3i as a 0, we also know that its conjugate, negative 3i, is a 0. So we have two zeros. We know two of them already, and we also know two of the factors. We know that if 3i is a 0, we know that x minus 3i has to be a factor. And if negative 3i is a 0, we know that x plus 3i has to be a factor. So we have two of our factors. We only need to find one more factor. And the reason that we have this is going to be really important. So let's go ahead and do the synthetic division. This is our value of k, 3i. We're going to set up our synthetic division algorithm. And we're going to see why this conjugate theorem is important once we get our quotient. So we bring down and we multiply. 3i times 1 is 3i. Negative 2 plus 3i, well, that's our term, so we can't combine them. We just have to write it as the complex number, negative 2 plus 3i. Then we're going to multiply 3i times negative 2 plus 3i. And we're going to do that over here on the side so we have some space. Negative 6i. This gives us 9i squared. Well, remember 9i squared, I squared is negative 1, so we actually have negative 6i minus 9. And then we want to write it back in standard form. So we have negative 9 minus 6i. And then we can go ahead and add 9 to negative 9. That gives us 0, so we're left with just negative 6i. And then when we multiply 3i times 6i, we get negative 18i squared, which again equals positive 18, giving us that remainder 0 that we need. So again, we just proved that 3i is a 0. And so now we have our new quadratic. Now this quadratic, you don't need to write this down, but this quadratic is kind of awful. Imagine trying to factor x squared plus negative 2 plus 3i x minus 6i. Those coefficients and constants aren't real numbers, so we can't factor it in our normal traditional methods. But luckily for us, we can continue to do synthetic division by using this conjugate 0 that we've been given. And we can do negative 3i as that conjugate 0 from before, and then use our coefficients of 1, negative 2 plus 3i, and negative 6i in order to continue factoring that quadratic. And so we bring down, we'll multiply negative 3i times 1 is negative 3i. When we combine these like terms, the 3i and the negative 3i cancel, leaving us with negative 2. Then we multiply negative 2 by negative 3i, and we get positive 6i. And those will cancel, leaving us with a remainder of 0. And again, now we have a new quotient right here, which is just going to be x minus 2, because we're going down 1 degree from where we started. So we have this factor of x minus 2. Combine that with the other two factors that we got earlier, and we have all three of our factors of x minus 3i, x plus 3i, and x minus 2. Fun fact as well is that if we were to want factors of only real values, we could multiply these back together, and what you're going to find out is that we're actually going to end up with a sum of squares. We're going to have x squared plus 3ix minus 3ix minus 9i squared. When we simplify, those cancel, leaving us with x squared plus 9. So if we wanted it factored with our real factors, we would have x minus 2 and x squared plus 9. So it just depends on what the question wants, whether it wants the linear factors. We call these linear factors. And these are going to be real factors, real number factors. Okay, where we're looking with coefficients and constants that are real. So again, it just depends on what the question wants. If we're looking for linear factors, we're going to stick with those non-real values, x minus 2, x minus 3i, and x plus 3i. If we want factors to only include real coefficients and constants, then we need to make sure that we multiply those complex conjugates together. Now this leads into our rational zeros theorem. Every time we've been trying to factor, we've been given a 0 or a factor of the polynomial. Well, now what we're going to do is, well, what if we're not given any of the zeros? And so this is going to rely on what we call the p's over q's, p's over q's. So we have a factor, a polynomial. So a polynomial of any degree, that's all this says, a polynomial of any degree. Again, where we have integer coefficients, then p over q is going to be a rational number written in lowest terms. And if p over q is the 0 of f, then p, the numerator, has to be a factor of the constant term, and q has to be a factor of our leading coefficient. And so we take our p's over our q's and we write them as a ratio of the constant factors over the leading coefficient factors. And we're going to be writing a bunch of numbers, a bunch of fractions and integers. And in that list of integers is the zeros, the rational zeros of our polynomial. And so we see here we have this 4th degree polynomial, and we're asked to find all the possible rational zeros, find the actual rational zeros, and to factor it. But we're not given any of the factors or zeros like we've been given before. And so it's up to us in order to find them. Well, the p's over q's is where we start. So P is the constant term. Okay, remember this is the constant term. And then the leading coefficient is Q. So we're going to have 6 over 6. And then we want to list all the factors of these numbers. Well, all our factors of 6 are 1, 2, 3, and 6. But don't forget, we also have the positives and the negatives for both of these. And what we're going to do is we're going to run through each numerator and match it up with every single denominator to form a list of rational numbers. So 1 over 1 gives me 1. 1 over 2 gives me 1 over 2. 1 over 3 gives me positive 1 over 3. Then 1 over 6 gives me positive and negative 1 over 6. Now we're done with the 1. We're going to repeat the process with 2. We're going to repeat the process with 2, but if we end up with a number that we already have, once we simplify, we don't need to write it again. So 1 over 2, or 2 over 1 just gives me 2. 2 over 2 simplifies to 1. Well, I already have 1, so I don't need to write it again. 2 over 3, that's a new one, so we're going to write positive and negative 2 over 3. And then 2 over 6, well, that simplifies just to 1/3, and we already have 1/3, so we don't need to write it again. Now we're done with 2. We're going to repeat the process with 3. 3 over 1, that's a new number. So we have positive and negative 3. 3 over 2, that's a new number. So we're going to write it. That's positive 3 over 2. Then we've got 3 over 3. Well, that simplifies to 1, so we don't need to write it again. And 3 over 6 simplifies to 1/2. We already have that, so we don't need to write it again. And we're going to go down to the last value, which is 6, and repeat the process one more time. 6 over 1, that gives us 6. That's a new number. 6 over 2 gives us 3. We don't need to write it again. 6 over 3 gives us 2. We don't need to write it again. And 6 over 6 gives us 1. We don't need to write it again. So this long list here is a list of all the possible rational zeros. All the possible rational zeros. In order to find the actual rational zeros, we have to use the factor theorem, where we have to do synthetic division with these numbers and figure out which of these give us remainders of 0. Which of these numbers give us a remainder of 0? Well, that's going to be a lot of guess and check. So let's say, for example, that we pick one of the numbers at random. Let's pick negative 3, okay, or 3. Is 3 a 0? Let's write that over here. Is 3 a 0? Okay, we're just picking one at random and going to see if it works. We'll do synthetic division with the 3. We'll set up our algorithm. And we're going to go through and do the synthetic division. Okay, so we may need to use our calculator a little bit as some of these numbers get bigger. So we get 18. 11, 33. My brain isn't working today, so we'll just get 15, and then we get 45. And already now I can see that I'm not going to get a value of 0. This is going to give me 58, and there's no way this multiplies to give me negative 6, and this isn't going to give me 0. So I know this is going to be not 0. So I know that 3 is not a 0. No, 3 is not a 0. Okay, well, that doesn't help me. That doesn't get me any closer. So we need to keep checking. And so we're going to pick another number. Okay, now I'm going to cheat a little bit because I know one of them that's going to work. And let's pick 1 and see if that works. So we pick a 1 and we bring it down. 6, we get 6. We get negative 1. We get negative 1. We get negative 19, we get negative 19, we get negative 6, we get negative 6, we get 0. We know that 1 is a 0. So we did that. 1 is a 0. That works out. Great. Well, guessing and check can take a long time. So a better way to do it, a much more efficient way to do it, is we're going to use our graphing calculator to look at the graph and estimate which ones are most likely to be rational zeros. Most likely to be rational zeros. All right, so what we'll do is we're going to open up our graphing calculator, and we're going to graph 6x to the fourth power. Oopsies, let me fix 6x to fourth power minus 7x to the third minus 18x squared plus 13x plus 6. And we're going to graph it. And we're going to look, and let's zoom in a little bit. Let's zoom in right there in the center. And we can see here that we have a 0 at about 1. Well, that checks out because we know that 1 is a 0. We already proved that using synthetic division. So we know that 1 is likely to be a 0. This intercept over here looks like it's at about 2. Over here, we're looking at something close to either negative 1/2, most likely probably negative 1/3. Okay, and then over here, we're looking at about negative 3/2. Okay, so these are most likely to be our rational zeros based on where our x-intercepts are. So we can use this as a list for synthetic division. And we're going to go through these and factor to see which ones give us the remainders of 0. Well, we already did it with 1. Okay, we already did it with 1. We know that 1 works. And so we know that 1 is a 0. Now we can go through and we're going to check 2. Okay, so let's check 2. But instead of doing it with the original polynomial, every time we do synthetic division and we get a remainder of 0, we've factored our quadratic a little bit further, or I'm sorry, our polynomial. And so now I have 6x to the third minus x squared minus 19x minus 6. This is a new polynomial that's factored. So when I go to find a 0 and continue factoring, I can just use the new polynomial, coefficients and constant, so that it continues to be factored even more. And so now I can use this new list of numbers and repeat the process. And I see that 2 is indeed another 0 because I get this remainder of 0. And now I'm left with 6x squared plus 11x plus 3. Now that I have a quadratic, my options are I can either continue to do synthetic division with the numbers that we have left to see if I get zeros, but I don't need to. I have a quadratic. We know how to factor quadratics. We want a product of 18 and a sum of 11. That's going to give us 9 and 2. So we can take 6x squared plus 9x plus 2x plus 3, and we'll factor it. And now we have our linear factors. So we've got a little mix of everything here, so we need to make sure that we're getting all of the right stuff. So these are factors right here. Now, we have to have the number of factors equal to the degree of the polynomial. And since it's a fourth degree polynomial, we have to have 4 factors. So here's our first 2. Our second 2 factors are going to come from the zeros. So if 1 is a 0, that means that x minus 1 is a factor. If 2 is a 0, that means that x minus 2 is a factor. So all 4 of my factors, when I include those in, are 3x plus 1, 2x plus 3, x minus 1, and x minus 2. Those are all 4 of my factors. Now the problem also asks for the zeros. So we got our factors. The problem also asks for the zeros. Well, the zeros are going to be what happens when we get our x-intercepts. And we saw those on the graph. We know that 1 is a 0. We checked for that earlier. It worked. We know that 2 is a 0. We checked for that earlier. It works. And then if we set both of these equal to 0, 3x plus 1 and 2x plus 3, we're going to get the zeros of negative 1/3 and negative 3/2. And so we don't really have to do any extra work because we've got it factored and we know our list of possible rational zeros. So those are our actual zeros right there. So we've got our zeros and we've got our factors. Let's go ahead and do it one more time. So here's another polynomial, very similar but still different. We want to find and list all possible rational zeros. So we want p's over q's. And so our p value is 2, our q is a 6. So we have factors of 1 and 2, and then 1, 2, 3, and 6. And we're going to go through and list all of those out, again, with the positives and the negatives. So our list of possible rational zeros: positive -1, positive -1/2, positive and -1/3, positive and -1/6. Then we've got positive and -2, positive and -2 over 2 is just 1. We've already got that. So then we've got 2/3. And then 2 over 6 gives us 1/3, which we already have. So this is our list of possible rational zeros. Now we want to actually find the rational zeros, and we want to go ahead and factor it. And so instead of doing some guess and check, let's go ahead and go straight to the graph and see what's going to work for us. So we'll make this -6x to the 4th. We'll change the minus to a plus. 7x to the 3rd minus 12x squared minus 3x plus 2, and delete that extra 6. So there's our new polynomial, and let's graph it. Okay, so this is going to be a little bit different. I only see 2x intercepts. Okay, so let's go ahead and set this to the standard zoom so we can kind of see. All right, I don't know why my graph stopped. Let's try that again. Well, it looks like my graph kind of froze there, so we'll just do what we can. But it kind of looks like we've got a possible rational zero at -1/2. I apologize. I just realized that I put a negative in there for some unknown reason. I don't know why. So I went ahead and fixed the polynomial. It's positive 6x to the 4th plus 7x to the 3rd minus 12x squared minus 3x plus 2. And then when we graph it, we get something way better to look at. So let's zoom in a little bit. So it's a little bit easier to read. And we can see it looks like we have zeros somewhere around. This looks like maybe it's -2. And then we got -1/2. And then we got maybe 1/3-ish. And then looks like hopefully 1 there. So we just want to kind of pick the numbers that are a little bit easier to get. If we look a little bit over here, we can also kind of trace along the line and see, okay, yeah, that's about 1/3. Keep tracing. That's about 1. So we can go ahead and look and make sure and see what we got. And then we're going to go ahead and use our synthetic division to go ahead and prove these. Let's choose our integer values first, just to make it a little bit easier. Let's start with 1. Let's see if 1 is indeed a 0. Fairly confident that it is. There we go. 1 is indeed a 0. And through that property, we also know that x minus 1 is a factor. Now we've got a new polynomial. This is a 3rd degree polynomial. So we can go ahead and do synthetic division again with these new coefficients and constants. And we're going to do -2 and see if -2 is a 0, and it should be. But let's make sure. And that works out. We know that -2 is a 0, and therefore x plus 2 is a factor. Okay, so we've got that working out for us. And then we're left with 6x squared plus x minus 1. We have a quadratic, so we can go ahead and factor that. A product of -6, but a sum of 1 is going to give us two numbers, 3 and a -2. So we have 6x squared plus 3x minus 2x minus 1. So we get our final factor of 3x minus 1 and 2x plus 1. And those match up with the corresponding zeros that we had up here of 1/3 and -1/2. So now we have all of our factors, including the 2 we found in the beginning, as well as the 2 that we verified, the 2 zeros that we verified in the beginning as well. So we've got all of our factors. all of our zeros. And there we go. We have completely factored a couple larger polynomials.